The cosmos holds more secrets than we can possibly count. One of its most peculiar treasures is the Tadpole Galaxy, a stunning cosmic oddity shaped by a violent collision and now home to a menagerie of bizarre objects. By the end of this journey, you will have explored 50 of its strangest inhabitants, from runaway stars to hidden black holes. Why does a supermassive black hole there spin at such a bizarre rate? And what is the true nature of the ghostly objects drifting in its colossal tail? Which cosmic mystery do you think will be the most difficult to solve? Deep within the tadpole's head lies a chaotic, brilliant forge of creation. This is the giant starburst core, a region so ferociously active it outshines the rest of the galaxy. Here, stars are not born in quiet, isolated nurseries. They erupt in a frantic, almost violent firestorm of cosmic construction. The core glows with the light of millions of newborn suns, all screaming into existence at a rate that defies all normal galactic behavior. A typical galaxy like our own Milky Way might form 1 or 2 new stars each year. This core, however, is a production line of stellar birth, forging the equivalent of dozens of suns annually. This incredible frenzy is a direct consequence of the immense collision that shaped the tadpole. When galaxies merge, their vast clouds of gas and dust are violently compressed, like a giant hand squeezing a cosmic sponge. All that raw material suddenly finds itself in a pressure cooker of unimaginable scale, triggering a chain reaction of star formation that lights up the galactic core with an almost unnatural fire. What does this tell us about the galaxy's past? It is a living snapshot of cosmic violence. The tadpole's brilliant heart is not a sign of peaceful maturity, but a roaring echo of the catastrophic impact that gave it its peculiar, stretched-out shape. This core is the blazing scar of that ancient encounter, a testament to the fact that from destruction on a galactic scale can come an overwhelming burst of creation. Yet at the very center of this brilliant, star-forging heart lies a paradox. The galaxy's supermassive black hole is strangely quiet. For an object of such immense power residing in the middle of a star-forming frenzy, its voice is little more than a whisper. This is not the roaring engine we might expect. Instead of a voracious, bright beacon devouring all around it, we find an anomaly, a sleeping giant with a peculiar secret. Its spin rate is all wrong. Think of a black hole like a cosmic top. Most supermassive black holes spin at incredible speeds, their rotation twisted by the constant inflow of material over billions of years. But the tadpole's central black hole spins at a rate that is bizarrely, unexpectedly slow. It is a lethargic titan in a land of hyperactivity. This slow spin has a direct, visible consequence. It produces only a faint, flickering jet of energy. This jet is not the steady, powerful beam seen erupting from other active galaxies. It is more like a sputtering candle, sometimes flaring for a brief moment before dimming again, struggling to push back against the dense soup of newborn stars and gas that surrounds it. Why would the heart of such a violent, productive galaxy harbor such a quiet black hole? The collision that triggered the starburst may have also disrupted the steady flow of gas needed to feed the beast and spin it up. Or perhaps we are witnessing a brief, quiet moment in a long and turbulent life. This faint, flickering jet is a clue, a quiet signal from a deeply unusual object that challenges everything we think we know about how galaxies and their central black holes evolve together. This quiet black hole is not the only thing behaving strangely in the Tadpole Galaxy. The very framework that holds the galaxy together, its invisible skeleton of dark matter, is also deeply puzzling. We cannot see dark matter directly, but we can detect its immense gravitational pull on the stars and gas we can observe. In a typical galaxy, this dark matter forms a vast spherical halo that extends far beyond the visible edges, and its gravitational center neatly aligns with the galaxy's bright core. But the tadpole defies this expectation entirely. Its dark matter halo is lopsided, a cosmic imbalance where the invisible gravitational anchor does not line up with the brilliant starburst core we see. It is as if the galaxy's soul is slightly off-center from its body. This creates a profound mystery. Our best models of gravity and galaxy formation predict that dark matter and visible matter should be tightly coupled, especially after a collision. The violent merger should have stirred everything together, yet here they are, misaligned. What could cause this gravitational ghost to slip out of place? One possibility is that dark matter is not interacting with itself or with regular matter in the way we have always assumed. Perhaps it experiences a subtle, unknown force that allows its halo to lag behind the visible galaxy during a collision. Or maybe we are seeing the messy, incomplete aftermath of the merger, a temporary state where the dark matter is still settling into a new equilibrium while the visible material has already been compressed into the star-forming core. This lopsided halo is more than a curiosity. It is a direct challenge to our fundamental understanding of gravity and the mysterious substance that makes up most of the universe's mass. If our models cannot explain this simple misalignment in a nearby galaxy, what other cosmic secrets are we missing? Drifting through the immense, dark river of the tadpole's tail are entire cities of stars, ancient and alone. These are orphaned globular clusters, celestial monuments that were violently evicted from their galactic home. Picture a dense, glittering sphere containing 1,000,000 ancient suns, all bound together by gravity for billions of years. In a normal galaxy, such clusters orbit peacefully in the outskirts like distant suburbs, but here they have been cast adrift. They are the undeniable evidence of the galaxy's catastrophic past. During the colossal collision that formed the tadpole, the gravitational tides were so immense that they did not just pull out a stream of gas and dust. They reached into the very heart of the smaller galaxy and plucked out these ancient stellar cities, hurling them into the newly forming tail. Now they travel in solitude, isolated from the bright, chaotic core of their new parent galaxy. What must it be like within one of these orphaned clusters? The night sky for any hypothetical planet there would be utterly alien. Instead of a faint, milky band, the heavens would be dominated by a permanent, brilliant twilight from the countless neighboring stars, all packed closely together. The central black hole of the tadpole would be a distant, irrelevant speck, its faint jet invisible. These clusters are relics, some of the oldest structures in the universe, and now they find themselves on a one-way journey into the void. Their very existence raises a profound question. If a collision can so easily strip a galaxy of its oldest inhabitants, how many other cosmic orphans are drifting, unseen, in the vast spaces between galaxies? This tail is not just a stream of gas, it is a highway of lost history, carrying these glittering fossils to an unknown fate. This river of cosmic orphans is not the only place where the galaxy is losing its children. Far ahead of the tadpole's tail, a lone star is making an even more dramatic escape. It is a hypervelocity runaway, a single sun flung out of the galaxy at a speed so immense that the tadpole's gravity will never pull it back. This star is not drifting, it is fleeing, a solitary bullet shot into the emptiness of intergalactic space. Its trajectory points directly back to the galaxy's chaotic core, a clue to the violent event that launched it on its endless journey. The most compelling theory for its origin is a cosmic slingshot, a gravitational maneuver of unbelievable power. Picture this star, once part of a binary system, two stars orbiting one another. Their path took them dangerously close to the galaxy's quiet, supermassive black hole. The immense gravity of the black hole would have acted like a celestial catapult, tearing the binary pair apart. One star was captured, doomed to orbit the black hole forever, while its partner was flung away at a staggering fraction of the speed of light. This is not a gentle ejection, it is a violent expulsion, a gravitational robbery that converts the energy of a binary orbit into the raw, linear speed of a runaway. What would that moment of launch have been like? In an instant, this star was ripped from its companion and from its entire galactic neighborhood, its velocity suddenly amplified to over 1,000,000 miles per hour. The view from a hypothetical planet around this star would be one of profound and increasing loneliness. The Tadpole Galaxy would rapidly shrink from a brilliant, sprawling spectacle into a faint, receding smudge of light, soon to be lost against the backdrop of countless other galaxies. This hypervelocity runaway is more than just a fast-moving object. It is a direct tracer, a piece of evidence that allows us to map the otherwise invisible gravitational field of the central black hole. Its path tells a story of a past encounter with a sleeping giant, a brief moment of cosmic violence that forever changed one star's destiny. How many other such runaways have already escaped, traveling unseen through the dark voids between galaxies? This runaway star is a testament to the violent forces at play, but the tadpole's strangeness runs even deeper. Within its swirling arms, astronomers have pinpointed an object that defies all known categories of cosmic engines. It is an ultraluminous X-ray source, a name that barely does it justice. From a single point-like spot in the galaxy, this object blasts out more X-ray energy than 1,000,000 suns emit across all wavelengths combined. It is a cosmic blowtorch, shining with an intensity that should be impossible for anything other than a supermassive black hole, yet it is not at the galaxy's center. So what could possibly be generating such staggering power? The debate is fierce and points to two equally bizarre possibilities. The first is an intermediate mass black hole, a long-sought missing link in cosmic evolution. We know of small black holes, the remnants of dead stars, and we know of the supermassive monsters at galactic centers, but an object in between, weighing thousands of times the mass of our Sun, has been incredibly difficult to find. This ultraluminous source could be exactly that, a middleweight champion devouring material from a companion star at a ferocious rate, releasing those incredible X-rays in the process. The second possibility is even more mind-bending. It could be an ordinary neutron star, the crushed core of a dead star, but one possessing a magnetic field of almost unimaginable strength. We call these objects magnetars. Their magnetic fields are so powerful that they can actually twist the very structure of space-time around them. If a magnetar were feeding on a companion star, its magnetic field could funnel the incoming material onto its surface in such a concentrated way that it overpowers its own usual limits, creating X-ray emissions that break all the rules. This is called the propeller effect, where the magnetic field acts like a cosmic shield. But in this case, the shield is so strong it forces the material to glow with unbelievable brilliance. So which is it, a missing link black hole or a neutron star operating far beyond its design specifications? Each option challenges our understanding of physics. One represents a new class of object, the other a known object behaving in a way we thought was impossible. The true nature of this ultraluminous beacon remains one of the tadpole's most intense mysteries, a tiny point of light forcing us to rewrite the textbooks on how the universe works. Even the most chaotic environments can give rise to objects of startling geometric perfection. Deep within the tadpole's turbulent spiral arms, a nebula glows with an almost unnatural symmetry. It is a near-perfect rectangle of crimson light, a cosmic structure so precise it seems deliberately crafted. This object is a direct analog to the famous red rectangle nebula in our own Milky Way, a twin separated by millions of light years, and its existence suggests that the laws of physics can sometimes paint with a ruler. The vibrant red color comes from a specific type of organic molecule known as polycyclic aromatic hydrocarbons. These are complex, carbon-based compounds that fluoresce with a deep red glow when bathed in the intense ultraviolet light from the central stars. They are essentially the same kind of molecules found in soot from a candle flame, but here, on a cosmic scale, they form the bricks and mortar of this beautiful, haunting structure. So how does nature, which so often favors spirals and spheres, create such a sharp-edged form? The secret lies in the delicate dance at its very heart. Two elderly stars, a binary pair, orbit one another in a tight, intimate embrace. As they age, they shed their outer layers in a continuous, dense wind of gas and dust. But the gravitational tug-of-war between the two stars shapes this outflow. Instead of expanding in a simple sphere, the ejected material is funneled into two cones, their tips touching at the binary system. From our distant vantage point, looking directly down the barrel of these cones, the edges appear to form a perfect rectangle, a cosmic illusion of stunning clarity. This is not a static sculpture, however. It is a fleeting masterpiece. The entire nebula is a preplanetary nebula, a brief and glorious phase in a star's life that lasts only a few thousand years. It is the final, beautiful sigh of a dying star system before it eventually cools and fades, leaving behind only a white dwarf at the center of the dispersing cloud. The presence of this geometric marvel in the Tadpole Galaxy tells us something profound. Even amidst the chaos of a recent galactic collision, the fundamental, delicate processes of stellar death and rebirth proceed with the same mathematical precision found in calmer galactic neighborhoods. It is a reminder that order and chaos are not opposites in the cosmos but constant companions. What other perfect shapes are hiding in the turbulence waiting to be seen? Amidst the galaxy's chaos, a circle of pure creation glows with serene perfection. This is the ring of star-forming fire, a near-flawless loop of stellar birth that stands in stark contrast to the turbulent spiral arms around it. Unlike the frantic starburst in the galaxy's core, this ring is a monument of organized, synchronized ignition. Its shape is no accident. It is the cosmic echo of a single titanic event, a shockwave of unimaginable force that blasted outwards from the center of the ring, sweeping up interstellar gas and dust like a snowplow clearing a highway. This colossal wall of compressed material then collapsed under its own weight, triggering the simultaneous birth of thousands of stars along a perfectly circular front. At the heart of this ring, you would expect to find the object responsible for the cataclysm. Perhaps it was a supernova of unprecedented power, the death scream of a truly monstrous star. Or maybe it was a local concentration of dark matter that violently interacted, releasing a burst of gravitational energy. The cause remains hidden, but the effect is breathtakingly clear. Within the ring itself, the stellar population is bizarrely uniform. These are not the mixed ages of stars you find in a typical cluster. They are almost all the same age, a single generation of stellar siblings forged in the same instant of cosmic violence. And they are not just any stars, they are predominantly massive, brilliant blue giants, stars that live fast and die young. Their intense ultraviolet radiation causes the entire ring to fluoresce, making it one of the brightest and most distinct features in the entire tadpole. What would it be like to have a planet inside this ring of fire? The night sky would be dominated by a continuous, blazing archway of newborn suns, a celestial hoop of light so bright it might cast shadows at night. The sheer density of massive stars means that supernova would be a regular, terrifying occurrence, each one potentially sterilizing any fledgling life on nearby worlds. This ring is both a cradle and a crucible, a place of magnificent birth that is also inherently unstable and short-lived. Its very existence raises a profound question about the galaxy's history. Was this a unique, one-time event, or is the Tadpole Galaxy prone to these rhythmic, explosive waves of star formation that leave behind perfect circles of fire as they expand and fade? This ring is a timestamp, a frozen moment of a galactic pressure wave that we are fortunate enough to witness before its brilliant, massive stars inevitably explode, scattering their enriched remains back into the void to one day form new worlds and perhaps new rings. Floating in the profound darkness between stars, a ghost haunts the tadpole's outer reaches. This is the ghostly hydrogen cloud, an immense and solitary structure of neutral hydrogen, gas so vast it could form millions of suns, yet it holds not a single one. It is a cosmic void of potential, a silent, starless expanse that should not exist according to our conventional models of galactic evolution. Its very presence forces a difficult question. Where did this colossal cloud, a celestial blank canvas, truly come from? One compelling theory paints it as a direct relic of the ancient collision. When the two galaxies merged, the gravitational turmoil would have been like a tidal wave washing through a sandy shore, pulling immense streams of gas far out into the void. This particular cloud could be one such strand, a tattered ribbon of primordial material that was stretched so thin during its expulsion that it simply never gathered the density required to ignite the fires of star formation. It is a fossil of the collision's violence, left hanging in space, frozen in time. The alternative is even more profound. This cloud may not be a product of the tadpole at all. It could be a pristine fragment of the intergalactic medium, a leftover building block from the dawn of the universe that is only now, by chance, being slowly drawn into the tadpole's gravitational embrace. We are potentially witnessing the galaxy's breakfast, a slow motion capture of raw, unprocessed material that has remained untouched by the stellar forges for over 13 billion years. How can we tell the difference? Astronomers listen to the cloud's whisper, analyzing the specific wavelength of radiation the hydrogen emits. Its velocity and chemical composition are the clues. If it moves in concert with the galaxy's tail and contains traces of heavier elements forged in ancient stars, it is likely a collision leftover. But if its motion is independent and its composition is purely primordial, a broth of only hydrogen and helium, then it is something far more rare, a direct window into the universe's simplest, most ancient state. This ghost is more than an empty cloud. It is a test of our ideas about how galaxies grow and where their material comes from. Is the tadpole merely rearranging its own furniture, or is it still gathering new lumber from the cosmic forest around it? The answer lies in the silent, dark heart of this wandering cloud. Even the galaxy's darkness can take a perfect form. A stark, diamond-shaped silhouette cuts across the tadpole's brilliant core, an opaque veil that stubbornly blocks our view into the galaxy's very heart. This is no amorphous cloud, but a precisely defined structure, a cosmic kite of dust and soot that hangs in space, casting a geometric shadow over the furious starburst happening beyond. Its sharp edges tell a story of immense forces and delicate balance. The lane is composed of tiny, carbon-rich grains, similar in size to particles of smoke mixed with frozen ices. But it is the sheer density of this material that creates such an profound shadow, absorbing the visible light from millions of stars behind it and irradiating it as a faint, warm glow in the infrared part of the spectrum. To an optical telescope, this region is a black void, an empty patch in the sky. But to an infrared observatory, the entire diamond glows with the heat of hidden stellar fires, a dark shape outlined by the energy it has stolen and transformed. How does such a geometrically perfect structure form and maintain its shape against the galaxy's chaos? The answer likely lies in a resonance, a gravitational rhythm set up by the collective orbit of billions of stars in the galactic bar. Just as a steady rhythm can make a jump rope settle into a stable pattern, the predictable gravitational tugs from the galaxy's overall structure can shepherd these dark dust grains into a fixed diamond-shaped orbit. It is a cosmic dance where gravity acts as the choreographer, arranging chaos into a temporary, breathtaking order. This dust lane is more than just a pretty obstruction. It is a vital clue to the conditions within the galactic core. By studying how its dust blocks different wavelengths of light, astronomers can map the hidden structure behind it, inferring the distribution of stars and gas we cannot directly see. It forces us to acknowledge that our view of the universe is always a filtered one, dependent on the tools we use to look. The diamond is a reminder that sometimes the most revealing features in the cosmos are not the brilliant lights, but the precise, dark shadows they cast. What other secrets are hidden behind similar veils in other galaxies, forever altering our perception of their true nature? A celestial clockwork ticks within the tadpole, marking time with flashes of cosmic violence. This is the recurrent nova system, a pair of stars locked in a deadly dance that erupts on a predictable schedule. One star is a white dwarf, the incredibly dense, Earth-sized core of a sun that has already died. Its partner is a larger, normal star like our own sun, but it is living on borrowed time. They orbit one another so closely that the white dwarf's immense gravity acts as a celestial thief, constantly stripping hydrogen-rich gas from the outer layers of its companion. This stolen material doesn't just fall onto the white dwarf's surface. It accumulates, piling up into a dense, hot, and increasingly unstable layer. For years, the pressure and heat at the base of this hydrogen ocean build silently. The white dwarf's surface becomes a bomb waiting to be lit. Then it happens. The temperature crosses a critical threshold, igniting a runaway thermonuclear explosion across the entire surface. In a matter of hours, the system's brightness can increase 50,000 times, outshining nearly every other star in the galaxy for a brief, spectacular moment. This is not a supernova which destroys the star. This is a surface blast that blows the accumulated material into space in a brilliant shell, leaving the white dwarf intact and ready to begin its thievery all over again. The cycle is relentless. The white dwarf survives, the donor star continues to bleed, and the stolen fuel begins to build up once more, setting the stage for the next scheduled detonation. What must it be like to witness such an event up close? The flash would be blinding, a second sun appearing without warning, bathing any nearby planets in a wave of lethal radiation before just as quickly fading away. The predictability of this eruption is what makes it so scientifically precious. Unlike the chaotic supernova that tear galaxies apart, this is a controlled experiment on a cosmic scale. Astronomers can mark their calendars for the next flash, using it to test theories of stellar evolution and nuclear physics with a precision impossible elsewhere. This recurrent nova is a reminder that some of the universe's most violent events are not random, but are governed by a strict, repeating rhythm, a metronome of creation and destruction set against the backdrop of an already chaotic galaxy. Another kind of time bomb ticks within the tadpole, one that doesn't flash with light but with invisible, lethal radiation. This is the Magnetar candidate, a neutron star so magnetically charged it warps the very fabric of reality around it. A neutron star is the collapsed core of a massive star that went supernova, a city-sized object so dense that a single teaspoon of its material would weigh billions of tons. But a magnetar is a neutron star pushed to an even more extreme. Its magnetic field is 1,000 trillion times stronger than Earth's, a force so incomprehensibly powerful it could strip the information from every credit card on our planet from halfway across the galaxy. This particular object doesn't announce itself with a steady glow. It sleeps for years or even decades, and then without warning, it unleashes a starquake. The crust of the neutron star, a rigid lattice of iron nuclei, suddenly fractures, releasing more energy in a fraction of a second than our sun will emit over 100,000 years. This energy erupts not as visible light, but in a blistering flash of gamma rays and X-rays, a burst that would be seen clear across the universe. For any hypothetical planetary system within a few light years, such an event would be an extinction-level catastrophe. The initial blast of radiation would scour the dayside of any world, instantly stripping its atmosphere and boiling its oceans. The aftereffects would be a prolonged death sentence, as the magnetar's outburst would violently ionize the surrounding interstellar medium, creating a toxic bubble that would prevent new star formation for eons. This object is a reminder that the universe's most dangerous entities are not always the largest, but those with the most concentrated volatile power. It is a dormant dragon, and its occasional furious twitches render an entire sector of the Tadpole Galaxy a cosmic dead zone. A splash of impossible blue stains the galactic canvas, a brilliant droplet of pure stellar youth. This is the blue blob, a stellar nursery so compact and ferociously active it glows with an almost electric intensity. Its color is the unmistakable signature of extreme heat, a visual scream from countless newborn massive stars. These are not the gentle, long-lived suns like our own. These are O-type and B-type giants, stellar behemoths that burn through their nuclear fuel in a cosmic blink just a few million years. Their surface temperatures are so scorching that they emit most of their light in the blue and ultraviolet part of the spectrum, bathing the entire nursery in this harsh, beautiful azure light. The environment within the blob is one of constant, violent creation. The fierce ultraviolet radiation from these young titans does more than just provide light. It ionizes the vast clouds of hydrogen gas from which the stars were born, causing the nebula itself to fluoresce in a self-made cage of light. But the stars are not content to simply shine. They are also blowing themselves apart, expelling their own outer layers in powerful, continuous gales known as stellar winds. These are not gentle breezes. They are supersonic hurricanes of charged particles, streaming away from the stars at speeds of millions of miles per hour. The collective effect of these winds is like a cosmic sandblaster, carving cavities in the surrounding gas and pushing the leftover material into dense, pressurized shells. In these compressed walls, the next generation of stars is already being triggered into existence, a chain reaction of birth driven by the violence of the first. What would it be like to float at the edge of this blue crucible? The sky would be a searing, uniform sapphire with no dark space between the stars. The stellar winds would create a constant, deafening roar across the electromagnetic spectrum, a soundless symphony of raw power. Any planets attempting to form here would be bombarded by radiation and scoured by these relentless gales, their potential atmospheres stripped away before they could even properly coalesce. The blue blob is a spectacular, self-limiting fire. Its very brilliance is a promise of its own rapid demise. In a few million years, the most massive of these stars will begin to explode as supernova, their death seeding the region with heavy elements and unleashing shockwaves that will likely trigger another, even more spectacular wave of star formation elsewhere. This tiny blue droplet is a single, brilliant frame in the grand, ongoing movie of galactic evolution, a fleeting moment of intense creation that shapes the future chemistry of the entire Tadpole Galaxy. The brilliant chaos of the Tadpole Galaxy can even warp the light of the distant universe. A quasar billions of light years behind it acts as a perfect cosmic beacon, its light bent and magnified by the tadpole's immense gravity. This phenomenon, a gravitational lens, should create a predictable, symmetrical ring of distorted images around the galaxy, but the ring we observe is subtly flawed. It bears a distinct kink, a small but undeniable warp in its perfect geometry. This tiny imperfection is a massive clue. It signals the presence of a hidden, incredibly dense object drifting within the tadpole's spiral arms, an object with enough gravity to twist the lens itself. Think of it as looking through a perfect, smooth magnifying glass and suddenly noticing a small, sharp flaw in the glass that distorts one part of the image. That flaw is the gravitational signature of something massive, dark, and compact. The leading suspect is a rogue black hole, one with the mass of 1,000 suns, wandering alone through the interstellar void. It is not at the galaxy's center, nor is it actively feeding and glowing. It is a dark, solitary hunter, its presence revealed only by the way its gravity pinches the fabric of space-time, leaving a fingerprint on the light passing by. Another possibility is a failed galaxy, a dark matter halo so dense and concentrated that it mimics the gravitational pull of a black hole, yet contains almost no stars to give it away. This lensing anomaly is more than a curiosity. It is a direct method for mapping the invisible skeletons of galaxies. We are not just seeing the tadpole stars and gas, we are seeing the intricate landscape of its total gravity, light revealing darkness. How many other dark, massive ghosts are drifting unseen through this and every other galaxy, their presence only detectable when they pass in front of a more distant star? Deep within the tadpole's spiral arm lies a cosmic graveyard, still glowing with the aftermath of a stellar death. This is the supernova remnant, a vast, expanding cloud of shattered star stuff, its filaments still racing outward at thousands of kilometers per second. It is the final, beautiful testament to a star that lived fast and died young, a titan whose explosive end seeded the galaxy with the heavy elements needed for planets and life. But at the very heart of this chaotic wreckage, something even more extraordinary is at work. A pulsar, the crushed core of that dead star, spins at an unbelievable rate, a dizzying cosmic lighthouse. This city-sized sphere of pure neutrons completes dozens of rotations every single second, and with each turn, it sweeps the universe with a blistering beam of radiation. The energy it releases does not just vanish into the void. It slams into the surrounding cloud of supernova debris, creating a second, nested nebula within the first. This is the Pulsar Wind Nebula, a glowing aura of light powered entirely by the pulsar's furious spin. Imagine the pulsar as a powerful motor, churning out a relentless gale of ultra-relativistic particles, a wind made of electrons and protons moving at nearly the speed of light. As this wind collides with the slower-moving material of the supernova remnant, it is abruptly slowed, and its immense kinetic energy is transformed into a brilliant, shimmering glow that we see across vast distances. It is a ghost inside a ghost, a nebula born from a nebula. This intricate structure is a cosmic clock telling two different times. The outer shell of the supernova remnant tells us about the moment of death, the single, violent event that occurred centuries ago. But the Pulsar Wind Nebula tells us about the ongoing life of the corpse, the energy it is still pouring into the universe today. The pulsar is slowly, inevitably spinning down. Its furious winds will one day cease, and the inner nebula will fade, leaving the outer shell to continue its slow expansion into the galaxy. This celestial Matryoshka doll is a fleeting phenomenon, a snapshot of a dynamic relationship between a dead star's legacy and its active, beating heart. What other such engines are hidden within the tadpole's many ruins, their inner light waiting to be seen? Drifting in the profound cold of the tidal tail, a dark and solitary wanderer makes its home. This is the intergalactic tramp, a rogue planet or a failed star known as a brown dwarf, cast adrift in the emptiness between galaxies. It is a world without a sun, a perpetual exile on a journey that will last for eternity. How did this lone object find itself so far from the warm embrace of a star? Its origin story is one of cosmic violence. It was likely born within the Tadpole Galaxy itself, part of a normal solar system. But during the galactic collision, the gravitational chaos was immense. A close pass to a massive star, or perhaps even the supermassive black hole, could have acted like a cosmic slingshot, flinging this planet or brown dwarf out of its orbit with such force that it achieved escape velocity, not just from its star but from the entire galaxy. In a single, violent moment, it was evicted from its celestial neighborhood and sentenced to an endless, solitary voyage. Imagine the environment on its surface if it has one. There is no day, only an eternal, star-studded night. The Tadpole Galaxy itself would hang in the blackness above, a magnificent, receding swirl of light, a constant reminder of the home it can never return to. There is no sunrise to warm the frozen ground, no seasons, no weather beyond the deep chill of space itself. The only heat would come from its own internal, primordial warmth, slowly bleeding away into the vacuum over billions of years. For a brown dwarf, this internal glow is faint, a dull red ember in the darkness. For a smaller, Earth-sized rogue planet, the surface temperature would hover just a few degrees above absolute zero, a frozen wasteland where any atmosphere would have long since collapsed into ice on the ground. This tramp is more than just a curiosity. Its existence tells us that galactic collisions do not just rearrange stars, they can purge entire planetary systems, scattering countless such worlds into the intergalactic void. How many other dark, frozen worlds are drifting out there, unseen and unknown? This lone traveler is a testament to the fact that the universe can be a profoundly lonely place, and that a world can be born only to spend its entire life in the deepest, coldest dark. The galaxy's hidden heart may not be a solitary beast, but a pair of locked titans. Evidence is mounting that the tadpole's core harbors not one, but two supermassive black holes caught in a slow gravitational waltz. This is the ultimate relic of the ancient galactic merger, the final, unresolved consequence of that cosmic collision. When two galaxies become one, their central black holes are destined to meet. Drawn together by immense gravitational forces, they begin to orbit one another, a binary pair separated by a distance that could be as small as our own solar system. We cannot see them directly, but their presence is betrayed by the subtle, periodic wobble they impose on the surrounding stars. A careful analysis of the starlight from the galaxy's brilliant core reveals a distinct, rhythmic flicker, a telltale sign that the stars are being tugged back and forth by the invisible, dueling gravity of two colossal anchors. This dance is not silent. As these black holes spiral ever closer, they churn the very fabric of space and time, sending out ripples known as gravitational waves. These are not waves of light or sound, but literal distortions in the continuum, stretches and squeezes in reality itself. The frequency of these waves is currently too low for our present observatories to detect, a deep, cosmic hum just below our hearing. But their existence is predicted by Einstein's theory, and this binary system is a perfect engine for their production. Imagine the final moments of this dance. Over millions of years, the orbit will decay, the black holes drawing closer and closer until they finally merge in a cataclysmic event that will release more energy than all the stars in the observable universe combined in that single instant. That collision will send a thunderclap of gravitational waves roaring across the cosmos, a signal that may one day be detectable across billions of light years. For now, this quiet waltz continues, a slow-motion prelude to an unimaginable explosion. The presence of this binary system confirms a fundamental prediction of galaxy evolution, showing us that the tadpole is not a finished product, but a work in progress, its very core still unsettled from the violence of its birth. Even the galactic debris holds the potential for new life. Adrift in the tadpole's immense tail is a small, glowing ember of cosmic rebirth, a fragment so distinct it has earned its own peculiar name, the green pea. This is not a star or a nebula, but a tiny, compact galaxy in its own right, a clump of gas and stars glowing with a vivid, almost unnatural green hue. Its color is a direct signature of its ferocious activity. The green comes from a specific type of light emitted by ionized oxygen, a gas that glows with intense brilliance when bathed in the harsh ultraviolet radiation from newborn stars. This tiny fragment is a stellar nursery of incredible purity and violence, a pocket of raw creation isolated in the darkness of intergalactic space. Its resemblance to a class of galaxies seen at the very edge of the observable universe is uncanny. Those distant objects, known as green pea galaxies, are some of the earliest building blocks of the modern cosmos, small, chaotic clumps that existed when the universe was young and pristine. Finding an object with the same properties right here in our own cosmic backyard, inside the tadpole's tail, is like discovering a living fossil. It suggests that the same fundamental processes that built the first galaxies are still at work today, sparked into action by the violence of a galactic collision. This fragment is a potential seed. the immense cloud of gas it contains could, over billions of years, coalesce into a new, small dwarf galaxy, a satellite to the mighty Tadpole. It is a glimpse into the most modest yet most fundamental level of galactic construction. What would it be like to stand on a planet forming within this green pea? The sky would be a perpetual, luminous green, the color of the surrounding nebula from which your own sun was born. The Tadpole Galaxy itself would loom as a breathtaking backdrop, a reminder of the violent event that gave your tiny world its start. This little green ember is proof that from the wreckage of old giants, new cosmic societies can begin. A heartbeat of fire pulses deep within the tadpole, a rhythm measured not in seconds but in years. This is the mirror variable star, an elderly red giant in its final dramatic act. It breathes, its entire body swelling and shrinking over a cycle of many months, its brightness waxing and waning like a slow cosmic lighthouse. But this star is not just pulsating, it is dying, and it has cloaked itself in the evidence of its own demise. A vast, cold envelope of dust and gas, a cocoon of its own creation, stretches out for billions of miles around it. This shroud is so thick and extensive that it makes the star almost invisible in ordinary light, yet it glows with an intense, radiant heat in the infrared, ranking it as one of the brightest such sources in the entire galaxy. The process is both beautiful and tragic. With every pulsation, the star's outer layers loosen, and powerful stellar winds carry this material away into the void. As this gas travels outward, it cools, allowing tiny particles of silicate dust, like fine grains of cosmic sand, to condense. This dust then drifts further, forming the immense opaque envelope that now defines the star's appearance. Think of a dandelion releasing its seeds to the wind, but on a scale so grand it defies human comprehension. This is not a gentle shedding, it is a systematic, unstoppable unraveling. What would it be like to approach this stellar elder? From a distance, it would appear as a faint red ember, but moving closer, you would enter a perpetual, blinding dust storm. The star itself would be a hazy, angry orb at the center of a dull, crimson glow, its light strained and reddened by the trillions of dust particles surrounding it. There is no clear sky here, only a suffocating fog of the star's own expelled substance. This vast envelope is a crucial recycling mechanism for the galaxy. The dust grains forming within it are rich with heavy elements like carbon, oxygen, and silicon, the very stuff of planets and life. When the star finally concludes its life, this entire shroud will be blown away, seeding the surrounding interstellar medium with the raw materials for new solar systems. The mirror variable is not just a dying star, it is a silent, breathing factory, manufacturing the fundamental ingredients of future worlds with every labored pulse. How many such celestial factories are quietly at work, their contributions unseen except as a faint, warm glow in the darkness? A stark black smudge stains the brilliant tapestry of a glowing nebula, a hole punched in the fabric of light itself. This is the dark globule, a small but impossibly dense knot of gas and dust so thick it allows no visible light to pass through. It stands in silhouette, a cosmic ink blot against the radiant background, a place where the universe has drawn its own curtains. Yet within this profound darkness, a secret and silent process is underway. The very opacity that hides it from our eyes is also its greatest tool for creation. The dust blocks the harsh ultraviolet radiation from nearby stars, creating a pocket of deep cold and calm. Inside this protective shroud, the relentless pull of gravity can work undisturbed. Slowly, inexorably, the cloud begins to collapse upon itself, fragmenting into even denser cores. Within these darkest of wombs, the first faint whispers of new stars begin to stir, their nuclear furnaces flickering to life in total secrecy. What would it be like to witness the birth happening inside? For eons, there would be only an increasing warmth in the absolute black, a gathering pressure. Then a point of light would ignite, but its glow would be immediately swallowed by the surrounding dust, transformed into a gentle, trapped heat that further encourages the collapse. These infant stars, called protostars, are cocooned in their own natal material, growing in the dark until they become powerful enough to blow their dusty cradle away. This tiny, dark blot is a perfect cosmic paradox. It is a place of shadow that exists only to create new light, a silent nursery where the future of the galaxy is being written in the dark, far from prying eyes. How many other such hidden cradles are scattered throughout the tadpole, their brilliant children waiting for the moment to tear through the veil and announce their presence to the universe? Even the most reliable cosmic beacons can sometimes send a confusing signal. Drifting through one of the tadpole's spiral arms is a pulsating giant known as an anomalous Cepheid variable, a star that should be a perfect standard candle for measuring the vast gulfs of space, but instead flickers with a puzzling inconsistency. Cepheid variables are the mile markers of the universe. Their true power lies in a beautiful, simple relationship between their pulse and their power. The longer it takes the star to brighten and dim, the greater its true intrinsic brightness. By comparing this known intrinsic brightness to how dim it appears from Earth, astronomers can calculate its distance with remarkable precision. This period luminosity relationship is a fundamental rung on the cosmic distance ladder, the very tool that allowed us to first grasp the scale of our galaxy and the expansion of the cosmos. But this particular Cepheid in the tadpole is broken. Its pulse, its steady rhythm, does not align with its actual brightness. The math simply does not add up. It is as if a lighthouse with a predictable flash sequence was suddenly shining with the wrong intensity, making it impossible to tell if it is a nearby beacon or a faraway giant. So what could throw off such a dependable cosmic clock? The star may be losing mass. If it is shedding its outer layers in a strong stellar wind, this could affect both its pulsation and its apparent brightness, tricking our instruments. Or perhaps it is not a single star at all, but a binary system where the light of a companion star contaminates the measurements, muddying the clean relationship we depend on. The most intriguing possibility, however, touches on the star's very composition. This Cepheid might have an abnormal mix of heavier elements, a different recipe of oxygen, carbon, and iron than the stars we use to calibrate the distance ladder in our own galactic neighborhood. Its internal nuclear furnace might run at a slightly different temperature or pressure, altering the physics of its pulsation. This single, misbehaving star in the Tadpole Galaxy forces a profound and unsettling question. If our most trusted cosmic yardstick has even one flaw, how accurately have we measured the universe? The anomaly does not just challenge our map of the tadpole, it introduces a tiny, nagging uncertainty into the scale of the entire cosmos, suggesting that some of our most fundamental distances might need a subtle but crucial recalibration. The light from distant stars carries hidden messages written in the language of absorption. When astronomers dissect the starlight shining through the Tadpole Galaxy, they find a series of mysterious, broad, dark bands superimposed on the spectrum. These are the diffuse interstellar bands, and they represent one of the longest-standing unsolved mysteries in all of astrophysics. For nearly a century, we have known these bands exist, yet we still cannot definitively identify the substance that creates them. They are the cosmic equivalent of finding a set of identical, complex fingerprints at every crime scene across a continent, but having no idea who the suspect is. The patterns are too broad and smooth to be from simple atoms or small molecules like those found in common space gas. The culprit must be something larger, more complex, and astonishingly widespread. The leading theory points to large, carbon-based molecules, perhaps similar to polycyclic aromatic hydrocarbons, but these are thought to be responsible for other, specific features in the spectrum. The true identity of the diffuse interstellar band carrier remains elusive. It could be vast, floppy molecules known as carbon chains, or even fullerenes, the famous buckeball molecules shaped like soccer balls but floating in the emptiness of space. The sheer ubiquity of these bands is what makes them so profound. They are not confined to one nebula or one dusty lane. They are seen everywhere we look in the tadpole and indeed throughout our own galaxy and others. This unknown substance is a fundamental yet invisible component of the interstellar medium, a pervasive cosmic contaminant that blankets the galaxy. What would it be like to fly through a cloud of this material? You would see nothing with the human eye. It doesn't block light like dust. It selectively siphons away specific, tiny slices of color from the starlight passing through it. Its presence is a ghostly chemical signature that we can detect but cannot name. Solving this puzzle is critical because this unidentified material is a major reservoir of carbon, the essential element for life. It is the hidden ingredient in the galactic recipe, and until we know what it is, we cannot fully understand how the raw materials for planets and living organisms are distributed throughout the cosmos. The diffuse interstellar bands are a quiet, persistent hum of cosmic ignorance, a reminder that even the most basic components of our galaxy can still hold profound secrets. A natural laser beam of microwaves pierces the darkness of a stellar nursery, a cosmic amplifier of pure, coherent light. This is a cosmic maser, an object where the chaotic energy of a star-forming cloud is transformed into an intensely focused signal. The word itself is an acronym standing for microwave amplification by stimulated emission of radiation. It is the exact same principle as a laser, but operating at the longer, less energetic wavelengths of microwaves. The engine for this natural wonder is a dense, tumultuous cloud of gas, rich with specific molecules like water or methanol. These clouds are constantly being bathed in the intense infrared radiation from newborn, massive stars nearby. This energy pumps the molecules up, elevating them to a higher, excited state, much like winding up a spring. When a passing microwave of just the right frequency happens by, it triggers these wound-up molecules. They all release their stored energy in perfect sync, amplifying that initial microwave into a powerful, narrow beam. It is a chain reaction of light, a natural feedback loop that turns a whisper into a shout. Imagine a vast, dark cloud seemingly inert to our eyes, but if we could see in microwaves, we would witness brilliant, pinpoint beacons flickering within it, each one a lighthouse signaling a pocket of intense activity. These maser spots are not steady. They flare and dim as conditions in the cloud change, acting as real-time probes of the violent environment around infant stars. They are nature's own precision instruments, revealing the motions and densities of gas in regions too obscured by dust for ordinary telescopes to penetrate. This natural laser is a fleeting phenomenon dependent on the perfect and temporary alignment of energy and material. Once the central star blows away its natal cloud, the maser will vanish. For now, its powerful, pure signal cuts through the cosmic noise, a rare and brilliant point of order in the heart of chaos. A star is literally reinventing itself before our very eyes. This yellow supergiant is a cosmic chameleon, caught in the middle of a dramatic transformation that happens in a celestial blink. It was, until very recently, a vast and cool red supergiant, a bloated leviathan. Now it is actively shrinking and heating up, its color shifting towards a hotter, more intense yellow-white. This is not a slow, graceful aging process. It is a frantic, last-ditch effort by a dying star to stabilize itself, a race against time that few stars ever undertake so visibly. Imagine a hot air balloon that has been floating for years suddenly and rapidly deflating, its envelope pulling tight as the burner roars back to life. The star is doing something similar on an unimaginable scale, shedding its outer layers and contracting its core in a desperate battle against gravity. This entire volatile phase might last only a few hundred or thousand years, a mere instant in the multi-million-year life of such a massive star. Its instability makes it a prime candidate for a future supernova, a ticking bomb whose countdown we cannot precisely measure. The star's outer layers are now in a state of extreme turbulence, with titanic convection currents bringing material from the searing hot interior up to the surface in a violent, bubbling frenzy. This creates wild fluctuations in its brightness and a powerful stellar wind that carries the star's own substance away into space at incredible speeds. What would it be like to witness this change up close? The star's color would be visibly shifting over a human lifetime, its hue warming from a deep, rusty red to a brilliant, pale topaz. The sky from a hypothetical nearby planet would be utterly transformed, the gentle, red glow replaced by a harsh, blue-white light that would sterilize the surface in a wave of lethal ultraviolet radiation. This yellow supergiant is a living laboratory, offering us a rare glimpse into the final, frantic chapters of a star's life. It forces us to ask a profound question. Is this dramatic transition the final act, or is it merely a prelude to an even more spectacular demise? This clump of cosmic debris is not just drifting, it is gathering itself into something new. Within the sprawling river of the tadpole's tail, a particular knot of gas and stars has achieved a critical density. It is a tidal dwarf galaxy candidate, a city of matter born from destruction that is now fighting for its own gravitational independence. This is not a random cloud, but a structure with its own center of gravity, one that is slowly convincing the surrounding material to orbit it, rather than simply flowing with the tail's current. It contains enough mass, perhaps billions of times that of our own Sun, to potentially bind itself together permanently. The very existence of such an object turns our understanding of galactic evolution on its head. We used to think that large galaxies grew by consuming smaller ones, a top-down process of cosmic cannibalism. But here, in the tadpole's wake, we see the opposite. A large galaxy is giving birth to a smaller one, a bottom-up creation sprouting from the wreckage of a collision. The ingredients for this new entity were all stripped from the parent galaxies, a mix of ancient stars from their halos and vast reservoirs of primordial gas. Now, within this clump, that gas is beginning to cool and collapse, igniting its own first generation of native stars. These new suns are the clearest sign that this is more than just a temporary structure. It is a budding galactic society, establishing its own identity far from the bright lights of the core. What would it be like for a civilization to evolve in such a place? Their night sky would be dominated by the arching, brilliant stream of the tadpole's tail, a constant, glorious reminder of their violent origin. The central galaxy itself would be a distant, receding island of light. They would be a people born in exile, their entire world forged from the discarded material of a cosmic accident. This dwarf galaxy candidate is a living experiment, showing us that the universe is not only a place of destruction, but also of relentless, opportunistic creation. Will this clump hold together against the tides of intergalactic space, or will it slowly dissipate, its stars returning to solitude? The answer will determine whether we are witnessing the difficult birth of a new galaxy, or merely a beautiful, fleeting illusion of one. This cosmic flower blooms with a secret at its heart. A planetary nebula drifts in the tadpole, its intricate shell of glowing gas a final, beautiful testament to a star's death. But this one is different. At its center, where astronomers expected to find a single, dying white dwarf star, they instead found a stellar trio, a gravitational dance of three suns locked in a complex orbital embrace. The nebula itself is the ghost of the primary star, which swelled into a red giant at the end of its life and shed its outer layers into space. Those layers should have drifted away in a simple, expanding sphere, a perfect bubble of cosmic remembrance. The presence of the two companion stars shattered that symmetry. Their gravitational pull acts like invisible hands, tugging and sculpting the outflow of gas into a wildly asymmetrical shape. The nebula is not a smooth ring, but a tangled web of loops and knots, its delicate structure warped by the constant, competing tugs of its stellar masters. Imagine trying to blow a perfect smoke ring while two friends circle you, alternately pushing and pulling your arms. The resulting smoke cloud would be a chaotic, beautiful mess, a frozen record of their motion. That is precisely what we see here. The intricate patterns in the gas are a direct map of the orbital dance happening within. This triple system offers a rare and violent glimpse into the final moments of a star's life within a crowded family. The dying star did not expire in peace. It likely engulfed one or both of its companions during its red giant phase, dragging them through its outer layers and creating immense friction that ejected material in unpredictable, powerful jets. The companions, in turn, stripped away gas from the primary star, funneling it into disks and outflows that further contorted the nebula. What would it be like to witness this from a nearby world? The sky would be dominated by a glowing, twisted tapestry of light, its colors shifting as different gases fluoresce. At its center, not one, but 3 points of light would gleam, 2 of them locked in a tight, rapid dance, the third a faint, cooling ember. This celestial structure is tragically fleeting. In just a few tens of thousands of years, the gas will disperse into the void, becoming invisible, and the white dwarf will cool forever alongside its binary companions. For now, this triple-star nebula remains a stunning fossil, capturing the chaotic influence of gravity on a star's final breath. A silent, high-speed collision is reshaping part of the Tadpole Galaxy right now. Far from the chaotic core, a massive cloud of pure hydrogen is slamming into the galactic disk at hundreds of kilometers per second. This is not a gentle merging of material, but a cosmic car crash on an unimaginable scale, and the impact site glows with the fires of forced creation. This high-velocity cloud originated in the frigid emptiness between galaxies, a wandering relic from the universe's early days that has finally found a place to crash. As it plows into the tadpole's denser interstellar medium, the leading edge of the cloud experiences a shockwave of incredible force. Think of it like a snowplow hitting a deep drift where the gas at the boundary is suddenly and violently compressed. This compression is the primary trigger for star birth. The immense pressure squeezes vast, diffuse clouds of hydrogen, pushing them past their gravitational tipping point. Pockets of gas that were once too spread out to collapse now rapidly condense, their cores heating up until nuclear fusion ignites and new stars scream into existence. The result is a linear firestorm, a brilliant front of stellar newborns that precisely traces the edge of the impact. What would it be like to witness this event from a nearby star system? The approaching cloud would be invisible to the naked eye, a dark tide against the star field. The first sign of trouble would be a gradual brightening along the horizon of the galactic disk, a thin, sharp arc of blue-white light growing steadily more intense. Then would come the shockwave itself, not of sound but of radiation and charged particles, a tempest that would likely scour the atmospheres of any worlds in its path. This is a wave of creation that is also an agent of destruction, clearing the galactic neighborhood and starting entirely anew. The presence of this impact site challenges the idea that star formation is driven solely by internal galactic processes. Here, the catalyst is an external force, a chance encounter with a piece of intergalactic flotsam that is literally hammering the galaxy into creating new suns. How many other such invisible bullets are on a collision course with the tadpole, or even with our own Milky Way, their silent approach destined to one day ignite a firestorm in the dark? A brilliant ghost glows in the darkness, a cosmic secret written in the language of heat. This is the unidentified infrared object, a source of immense energy that remains stubbornly invisible to our eyes and optical telescopes, revealing itself only as a blazing beacon in the infrared part of the spectrum. It outshines entire star clusters in this thermal light, yet when we point our most powerful visible light observatories toward its location, we see nothing but an empty patch of space. It is there, but it is not, a profound contradiction that challenges our most basic tools for classifying cosmic objects. So what could possibly be so powerful yet so hidden? The debate centers on two equally compelling theories, each pointing to a radically different cosmic phenomenon. The first possibility is a dust-enshrouded supernova, a stellar explosion that happened deep inside an impossibly thick cocoon of cosmic soot. In this scenario, a massive star reached the end of its life and detonated, but the brilliant flash of visible light from the blast was completely absorbed by the surrounding dust. That energy did not vanish, however. It was absorbed by the dust grains, heating them to incandescent temperatures and causing them to irradiate all that captured energy as a torrent of infrared radiation. We are seeing the echo of a catastrophe, the thermal aftermath of a death we never witnessed directly. The second, even more exotic possibility is a nascent globular cluster in its very earliest stage of formation. Imagine a vast cloud of gas and dust, so dense that not a single photon of visible light can escape, collapsing under its own weight to form not one star, but hundreds of thousands of them at once. The fierce radiation from all these infant stars is immediately trapped by the natal cloud, turning the entire structure into a single, glowing ember in the infrared. We would be witnessing the birth of a glittering stellar city, but seeing only the warm, opaque shell of its cradle. How long will this object remain a mystery? Its future holds the answer. If it is a supernova remnant, the expanding shockwave will eventually blow the dusty shroud apart, and a more familiar nebula will emerge into view. If it is a protoglobular cluster, the intense stellar winds from its massive young stars will, over millennia, scour away the dust, revealing the brilliant blue cluster within. For now, it exists in a state of pure potential, a hidden engine of cosmic change whose true nature is known only to itself. This unidentified infrared object forces us to confront a fundamental truth about our place in the universe. We see only a tiny sliver of the cosmic drama, the narrow band of light our eyes can perceive. The real story is often playing out in the dark, revealed only by the gentle warmth it leaves behind. A faint, shimmering halo of light continues to expand from a point of ancient violence, a delayed broadcast from a star's death centuries ago. This is the light echo, a ghostly replay of a supernova that faded from direct view long before humans built telescopes. The original flash of light from the explosion raced outwards at, of course, the speed of light, and passed our planet long ago. But that initial burst also illuminated vast, distant clouds of interstellar dust that lie far behind the supernova's location. This light then reflected off those dust clouds, taking a longer, indirect path to reach us. We are now seeing that reflected light arriving centuries late and painting a series of faint, expanding rings on the sky. It is as if the universe itself is replaying the explosion for us in slow motion, giving us a second chance to study an event we otherwise missed entirely. Each ring corresponds to a different shell of dust, with the light from the outer rings having traveled a slightly longer path than the light from the inner rings. By carefully analyzing the spectrum of this echoing light, astronomers can dissect the physics of the original explosion, learning about the star's composition and the mechanics of its death long after the fact. What would it be like to float near one of those reflecting dust clouds? You would have witnessed a sudden, terrifyingly brilliant flash from a distant point, illuminating your entire cosmic neighborhood for a few weeks before fading, leaving only the normal starlight. Then, centuries later, astronomers in a far-off solar system would finally see that same flash reflected in your dusty sky. This phenomenon turns the galaxy's dust into a colossal set of mirrors, each one angled to show us a different moment from a single, catastrophic event. The light echo is more than a pretty ring. It is a time machine allowing us to interrogate the past and study the final moments of a star that died before our modern science even began. How many other such echoes are expanding silently through the tadpole, their faint light carrying stories of stellar deaths we have not yet learned to see? Some of the oldest living things in the entire universe drift silently within the tadpole's halo. This metal-poor star cluster is a pristine relic, a glittering city of suns so ancient they remember a time before most elements even existed. Their composition is staggeringly simple, almost pure hydrogen and helium with a mere whisper of anything heavier. This profound lack of metal is not a sign of poverty but of immense antiquity. These stars are first-generation pioneers, formed from the raw, unprocessed material left over from the Big Bang itself. To be metal-poor in astronomy is to be a living fossil, a direct window into the cosmos's earliest chapters. The very iron in your blood, the calcium in your bones, and the oxygen you breathe did not exist when these stars first ignited. Those heavier elements had to be forged in the nuclear furnaces of later stellar generations and scattered across space by supernova explosions. This cluster is a time capsule from an era before that cosmic enrichment began. What would the night sky look like from a planet orbiting one of these ancient suns? The constellations would be utterly alien, populated by stars that burn with a fierce, pure, blue-white light, largely free of the planetary systems that might surround them. The galaxy itself would appear smaller, darker, and far less structured, a primitive canvas awaiting the brushstrokes of later stellar deaths. The preservation of this cluster within the turbulent Tadpole Galaxy is itself a minor miracle. The colossal collision that shaped the galaxy should have torn such a fragile, ancient structure apart, scattering its stars into the general halo. That it survived suggests it was a bystander, orbiting far from the violent merger, and has only recently been captured by the tadpole's gravitational embrace. This cluster does not just tell us about the past, it serves as a critical baseline. By comparing its pristine stars to the metal-rich ones in the galactic core, we can measure the entire history of cosmic chemical evolution. It is the control sample in a galaxy-wide experiment, the simple beginning against which all later complexity is measured. How many other such primordial clusters are hiding in plain sight, their quiet light holding the untold story of everything that came after? A faint, unassuming red dwarf star in the Tadpole Galaxy suddenly screams. In mere minutes, its brightness increases by hundreds of times, a violent tantrum that briefly outshines stars many times its size. This is the flare star, a celestial demonstration that small size does not equal a quiet life. These eruptions are not gentle flickers but catastrophic magnetic storms on a global scale. The star's intense magnetic fields become tangled and stressed, storing energy like a wound-up spring. When the tension becomes too great, the fields snap and reconnect in a process of colossal short-circuiting. This event unleashes a firestorm of radiation across the entire electromagnetic spectrum, from radio waves to X-rays, and accelerates particles to nearly the speed of light. Imagine standing on a planet orbiting this star. One moment, you have a dim, crimson sun providing a perpetual twilight. The next, a searing, white-hot flash erupts, doubling the star's apparent size in the sky and bathing your world in a wave of lethal radiation that would instantly destroy any nascent life and strip away an atmosphere. The flare's peak is terrifyingly brief, often lasting only minutes before the star settles back into its usual faint glow, as if nothing happened, but the damage is done. These frequent, unpredictable tantrums ensure that the habitable zones around such stars are not safe harbors, but cosmic killing fields, sterilizing any planet within range on a regular basis. This violent behavior forces us to reconsider the nature of the most common stars in the universe. For every calm, stable sun like our own, there are countless others whose turbulent magnetic hearts make them unlikely cradles for life. The flare star is a powerful reminder that stellar violence is not the sole domain of massive giants, but can erupt from the smallest, most common suns, their quiet demeanor hiding a tempestuous and deadly nature. Around another young star, a celestial blueprint for a new solar system is being drafted in dust and gas. This is a protoplanetary disk, a vast, flat wheel of primordial material spinning in a delicate balance between the star's gravity and its own rotation. But this disk is not a smooth, featureless sheet. Cutting through it are a series of stark, dark rings like the grooves on a vinyl record. These gaps are not empty. They are the gravitational signatures of infant worlds, planets so young they are still hidden within the disk, yet already powerful enough to sculpt their own cosmic neighborhoods. Each gap represents the orbital path of a protoplanet. As this nascent world, a ball of rock and ice perhaps no larger than our moon, travels around its star, its gravity acts like a cosmic snowplow. It clears a path through the finer dust and gas, herding the material either inward or outward, leaving a distinct, empty band in its wake. The very presence of these gaps is our strongest evidence yet for how planets are born. We are witnessing the construction phase of an entire planetary system, seeing not the finished planets themselves, but the shadows they cast and the paths they carve. What would it be like to stand on the surface of one of these forming worlds? The sky would be a perpetual, blinding orange from the glowing disk material above and below you. The central star would be a fierce, young sun, prone to violent flares, its light filtering through a thick, dusty haze. You would be standing on a world still under constant bombardment, a place where the very ground beneath your feet is still cooling and solidifying from its violent accretion. This disk is a dynamic and fleeting structure. Within a few million years, the remaining gas will be blown away by the young star's intense radiation. The dust will either coalesce into more planets or be swept up by existing ones, and the clear, dark gaps will vanish, leaving behind a mature solar system of planets orbiting in the clean emptiness of space. For now, this cosmic construction site offers us an unprecedented view into our own distant past, a time when our sun was also surrounded by a dusty disk, and the Earth was nothing more than a clear path in the chaos, a promise waiting to be fulfilled. A miniature cosmic powerhouse unleashes its fury within the Tadpole's spiral arm. This is the Galactic microquasar, a stellar system that perfectly mimics the most energetic objects in the universe, but on a scale we can almost comprehend. At its heart lies either a stellar mass black hole or a neutron star, a remnant of a dead star. This dense corpse is not alone, it has a companion, a normal star that is slowly being consumed. The black hole or neutron star's immense gravity acts as a relentless thief, stripping gas from its partner and pulling it into a swirling, superheated disk of doomed material. As this plasma spirals inward, it is compressed and heated to millions of degrees, glowing with intense X-rays, but the true spectacle happens at the poles. Some of this infalling material, instead of crossing the event horizon, is channeled by powerful magnetic fields and blasted back out into space in two narrow, opposing jets. These are not gentle outflows, they are relativistic jets propelling matter at over 99% of the speed of light. The energy required to accelerate material to such a velocity is almost beyond imagination, a testament to the ferocious physics at play just a few miles from the central object. What would it be like to witness this up close? The jets would appear as two infinitesimally thin, blindingly bright beams of energy stretching for light years, a cosmic blowtorch on a scale that dwarfs entire solar systems. The system would flicker and flare as the rate of accretion changes, its X-ray brightness varying wildly over days or hours. This microquasar is a perfect nearby laboratory. The quasars at the centers of distant galaxies are powered by supermassive black holes billions of times heavier than our Sun, their jets stretching across millions of light years. Their immense distance and complexity make them difficult to study in detail, but this microquasar in the Tadpole operates on the exact same principles, just with a smaller engine. By observing its relatively rapid changes and closer proximity, we can test our theories about how accretion disks form, how jets are launched, and how these cosmic engines convert gravitational energy into raw, focused power. This tiny, brilliant object is a scale model of the universe's most violent phenomena, a roaring whisper that teaches us the language of giants. This star is a cosmic alchemist, transforming simple elements into the building blocks of soot. Object 34 is a carbon star, an elderly red giant that has achieved a remarkable and beautiful internal imbalance. While most stars, including our own Sun, have atmospheres richer in oxygen than carbon, this one has flipped the recipe. Through processes deep in its interior, carbon has been dredged up to the surface, becoming the dominant heavy element in its outer layers. This surplus of carbon fundamentally changes the star's chemistry and its appearance, casting it in the deepest, most profound crimson hue. The carbon atoms readily link together in the cool outer atmosphere, forming sturdy molecules that act as light filters. These molecules absorb the blue and green parts of the star's light, allowing only the reddest wavelengths to escape into space. The effect is a gem-like glow, a point of deep ruby fire in the telescope's eye. But the star's work does not end with coloring itself. The carbon continues to link into ever larger chains, eventually forming solid particles not unlike the soot from a candle flame. This soot condenses in the star's expansive, gently flowing stellar wind, creating a vast, dark shroud of carbon dust that drifts outwards for billions of miles. This is more than just cosmic dirt. These carbon grains are the raw materials for future possibilities. They will eventually be blown into the interstellar medium, where they may one day become part of new planetary systems, perhaps even the core of rocky worlds or the complex molecules that lead to life. What would it be like to stand on a world orbiting this star? The daylight would be a perpetual, unsettling blood-red twilight, casting long, dark shadows. The night sky might be filled with a faint, orbiting veil of this newly minted soot, occasionally dimming the other stars as it passes. This carbon star is a temporary factory, a brief but crucial phase in the galactic recycling program that takes the helium forged in stellar cores and transforms it into the carbon that is essential for all known life. Its deep red light is a beacon, signaling a fundamental change in a star's life and its contribution to the chemical richness of the cosmos. A newborn star announces its arrival not with a gentle glow but with a violent scream of light. This Herbig-Haro object is a cosmic flare, a temporary beacon marking the brutal process of stellar birth. It begins with a protostar, a sun still gathering mass from its dusty cradle. As the star forms, it doesn't just pull material in, it also spits a significant portion back out in two incredibly focused supersonic jets erupting from its poles. These are not gentle winds, they are narrow, high-velocity bullets of plasma, racing away at hundreds of kilometers per second. When these jets slam into the slower-moving clouds of gas and dust surrounding the infant star, the collision is catastrophic. The energy of the impact heats the gas to millions of degrees, causing it to fluoresce with a brilliant, shimmering glow. Each of the bright knots you see in the nebula is a separate shock front, a cosmic traffic jam where the star's relentless jet is plowing into the interstellar medium. The entire structure is a constantly changing battlefield. The central protostar is still actively feeding, so its jets can flicker and vary in intensity, causing the glowing patches to brighten and fade over just a few years. What would it be like to witness this up close? You would see two opposing beams of raw energy stretching for trillions of miles, punching into the nebula and lighting it up from within like a cosmic flare gun. The soundless roar of these collisions would be written across the electromagnetic spectrum, a cacophony of energy signaling a star fighting its way out of its dusty womb. This beautiful, violent object is fleeting. In a few tens of thousands of years, the central star will stabilize, its jets will shut off, and the brilliant nebulosity will fade, leaving behind a mature star and a cleared-out space around it. For now, this Herbig-Haro object is a perfect snapshot of stellar adolescence, a brilliant and short-lived tantrum that illuminates the chaotic first steps of a sun's life. This star is a cosmic titan living on the edge of self-destruction. A luminous blue variable is so massive and brilliant it struggles to hold itself together, a hypergiant perpetually trembling on the verge of exploding. Its instability is not a quiet flaw but a defining, spectacular characteristic. For decades at a time, it may shine with a deceptive calm, a brilliant blue-white beacon in the galactic darkness. Then, without any discernible pattern, it erupts. These are not mere flares, but giant outbursts where the star violently expels its own outer layers into space, shedding more mass in a single event than our entire sun contains. Imagine a star having a feverish, existential crisis where it decides to literally throw pieces of itself into the void. The trigger is its own immense power. The radiation pressure burning outward from its core is so intense that it nearly overcomes the inward pull of gravity. This creates a precarious balance, and when that balance tips, the star's outer envelope is pushed out in a tremendous convective shudder, launching a shell of stellar material at incredible speeds. What would it be like to witness such an outburst from a safe distance? The star would swell in size, its color shifting as its surface cools slightly, and its brightness would skyrocket, potentially outshining every other star in its galactic neighborhood for months. A wave of expelled gas glowing with the energy of the event would expand outward like a cosmic tsunami, carrying with it the enriched remains of the star's interior. This is more than just a tantrum, it is a fundamental part of the star's rapid evolution. Each outburst strips away layers, bringing ever deeper, more fused material to the surface, like an onion unwrapping itself under cosmic duress. This behavior makes it a prime supernova candidate. We are essentially watching a star in its final, most volatile act, a prelude to the ultimate cosmic detonation. Its frequent mass loss is a desperate attempt to stabilize, but it is a fight it is destined to lose. When its core finally runs out of fuel, the collapse will be catastrophic, resulting in a supernova so bright it could briefly outshine the rest of the Tadpole Galaxy combined. This luminous, unstable giant is a ticking time bomb, and every outburst is another loud tick on the countdown to an inevitable, galaxy-shaking boom. A perfect circle of fire hangs in the void, a cosmic halo sculpted by gravity itself. This Einstein ring is one of nature's most precise demonstrations of warped space-time, a phenomenon predicted by Einstein a century ago and now seen in stunning detail within the Tadpole's neighborhood. The ring is not a real object but a trick of the light, an optical illusion on a galactic scale. At its heart lies a massive galaxy cluster, its immense collective gravity acting as a natural lens, bending the very fabric of space around it. When the light from a single, perfectly aligned background galaxy travels through this warped region, its path is curved. Instead of arriving at our telescopes in a straight line, the light is smeared and stretched into a brilliant circular pathway. We are seeing the same distant galaxy multiple times, its image replicated and wrapped around the lensing cluster to form this celestial crown. The perfection of the ring is a testament to a flawless alignment. The background galaxy, the foreground cluster, and our own vantage point must all be in near-perfect symmetry for the circle to appear so unbroken. A slight misalignment would create arcs or multiple fragmented images, but here, the geometry is so exact it produces a near-flawless ring of luminescence. What would it be like to exist in that background galaxy, looking back toward the tadpole? You would see your own light being bent around the cluster in a strange, gravitational mirror, a distorted view of your own cosmic home. This ring is more than a beautiful curiosity, it is a powerful scientific instrument. The amount of distortion reveals the total mass of the foreground cluster, including its vast reservoir of invisible dark matter. By studying the ring's precise shape, astronomers can literally weigh the cluster, mapping the distribution of both seen and unseen material with incredible accuracy. This single, perfect circle of light allows us to see the invisible architecture of the cosmos. proving that even the most ethereal forces leave a visible signature on the light that passes by. A spherical void large enough to swallow entire star systems drifts within the galactic disk. This is the supershell, a cosmic bubble of astonishing scale, its interior a near-perfect vacuum carved out by the collective fury of stellar titans. Imagine a cavity spanning hundreds of light years, a region so empty that if our solar system were adrift inside it, the nearest star would be an impossibly distant speck. The shell itself is a single, continuous wall of compressed gas and dust glowing faintly from the ancient violence that formed it. This structure is not the work of a single event, but a chain reaction of cosmic force. At its origin lies a massive OB association, a family of brilliant, short-lived blue giants. Each of these stars burns with a ferocious intensity, and each expels its outer layers in a powerful, continuous gale known as a stellar wind. For millions of years, these individual winds combined into a single, colossal outflow, a hurricane of charged particles that began pushing the surrounding interstellar medium outward, like a dozen fire hoses blasting against a cosmic sand dune. But the real sculpting force came from death. The most massive stars in the association lived fast and died young, exploding as supernova one after another. Each detonation delivered a hammer blow to the interior of the growing bubble, its shockwave slamming into the expanding wall and driving it ever outward. The supershell is the fossilized remnant of this stellar chorus, its final, brilliant shouts frozen in the architecture of space itself. What would it be like to travel through this void? The journey would be one of profound emptiness and eerie silence. You would pass through a volume of space containing almost nothing, a galactic desert where the normal thin soup of interstellar gas has been utterly swept away. The only sight would be the distant curving wall of the shell itself, a glowing, nebulous horizon in every direction, a constant reminder of the furious stellar nursery that once raged at the center. This bubble, however, is not just a scar. Its immense, compressed outer wall is now a perfect breeding ground for the next generation of stars. The very same forces that cleared this void have also triggered a new wave of creation at its edges, a stellar offspring that will one day likely repeat the entire cycle. The supershell is a cosmic engine of rebirth, proving that even the most destructive forces in the galaxy are ultimately agents of renewal. A silent, ghostly arc drifts through the Tadpole's radio sky, a whisper from a forgotten cataclysm. This anomalous radio loop is a colossal structure, a crescent of energy visible only to instruments that can see the universe in the long, cool waves of radio light. To our optical telescopes, this region of space appears utterly empty, a void between the stars. But when we tune into the radio spectrum, this immense loop suddenly materializes, glowing with the faint synchrotron radiation of electrons spiraling at near light speed through a weak magnetic field. It is the ghost of an event, the lingering echo of a shockwave that has long since faded from view. The sheer scale of this loop is what makes its origin so puzzling. It is not the neatly expanding shell of a recent supernova, nor is it the structured jet from an active black hole. Its morphology is more primal, a simple, vast arc that suggests a titanic, focused release of energy in the distant past. One compelling theory is that we are seeing the remnant of a hypernova, a supernova on steroids. This would be the death scream of a first-generation star so massive that its core collapse produced not just a stellar explosion, but two opposing jets of relativistic matter erupting from its poles. The radio loop could be the bow shock from one of these jets, a colossal bubble blown into the interstellar medium as the jet plowed through it and finally dissipated. Another, even more exotic possibility is that this loop is a fossil, the remnant of a tidal disruption event from an earlier cosmic era. Imagine a star wandering too close to an intermediate mass black hole. The black hole's gravity would shred the star, pulling it into a long, thin stream before consuming it. The incredible release of energy from such a meal could have launched a powerful outflow, whose shockwave expanded for eons before settling into this faint, radio-emitting relic we see today. What would it have been like to witness the birth of this loop? The initial flash would have been a second sun in the tadpole sky, a point of light so brilliant it would have outshone the galactic core for a few terrifying weeks. The afterglow, the expanding shockwave that now makes the radio loop, would have been visible for centuries as a slowly growing nebula before finally cooling and fading from optical view, leaving only this faint radio frequency memory. This silent arc is a cosmic cold case. The evidence is there, written in the spiraling paths of electrons, but the culprit and the exact moment of the crime are lost to deep time. It forces us to wonder how many other such ghosts are drifting through the galaxy, their stories waiting to be heard on frequencies just beyond our normal sight. A stellar infant is throwing a tantrum of cosmic proportions. This pre-main sequence star is a sun still in its earliest developmental stage, not yet powered by the steady fusion of hydrogen in its core. It lives by accreting mass, pulling in gas and dust from the vast spinning disk that surrounds it like a celestial crib. For the most part, this feeding process is a relatively steady trickle, a quiet siphoning of material. But then something breaks, the smooth flow is disrupted, and a sudden, massive clump of disk material, perhaps as large as a whole solar system, loses its orbital stability and plummets inward. When this enormous lump of gas and dust slams into the surface of the young star, the result is an accretion burst. The star's brightness can skyrocket by a factor of 100 in just a few days, a violent flash that temporarily outshines everything else in its stellar nursery. Think of a baby swallowing its food too quickly and letting out a tremendous burp of light. This is not a gentle process. The impacting material releases a staggering amount of gravitational energy, instantly heating a vast area of the star's surface to millions of degrees. The flash of radiation blasts out across the system, illuminating the inner regions of the protoplanetary disk and potentially vaporizing any fledgling planets that were forming too close. What triggers such a dramatic collapse of the disk? The culprit is likely gravitational instability. The disk itself, a swirling mass of gas and dust, can become so massive that its own gravity causes it to fragment. It develops clumps and knots, and when one of those knots grows too heavy to maintain its orbit, it surrenders to the star's pull in a single, catastrophic event. For astronomers, catching one of these outbursts is like finding a fossil mid-step. It freezes a critical moment in the life of a young solar system, revealing the violent, chaotic environment in which planets are born. This sudden infusion of mass might even affect the star's ultimate destiny, altering its final size and temperature. How many other such infant stars are lurking in the tadpole, their growth marked not by a steady glow, but by these brilliant, unpredictable fits of cosmic hunger? Even the debris of a cosmic wreck can host its own spectacular drama. Drifting in the immense river of the tadpole's tail is a pair of small, intertwined galaxies caught in a private dance of mutual destruction and creation. This is a collision within a collision, a nested echo of the same violent process that shaped the tadpole itself. These two dwarf galaxies, once separate island universes, are now so deeply entangled that their gravitational pull has stretched them into long, luminous streamers of stars, a miniature replay of the grander event that spawned their current home. Their individual identities are already lost, blurred into a single, chaotic structure that glows with the fires of new star formation ignited by their own private merger. What an incredible sight this must be from a hypothetical planet inside one of them. The night sky would be a shattered masterpiece, dominated not by a single, coherent spiral, but by the brilliant, distorted wreckage of the other galaxy, its stars stretched into great arches and shells across the heavens. The Tadpole Galaxy itself would loom in the background, a colossal, silent reminder of the larger-scale fate that awaits this merging pair. Their dance is a preview of the distant future. Just as the tadpole was formed from a colossal impact, this pair is on a path to become a single, larger dwarf galaxy, a new, stable entity born from the chaos of the tail. They are demonstrating a fundamental truth of the universe, that gravity is a relentless social force, constantly pulling structures together across every scale. This intimate merger also solves a practical mystery. The tadpole's tail is not just a stream of orphaned stars and gas, it is a fertile ground for the formation of new galactic structures. By watching these two galaxies merge, we see how the dwarf satellite galaxies that orbit large spirals like our own Milky Way might have themselves been assembled from smaller pieces in the distant past. This interacting pair is more than a curiosity, it is a living fossil of hierarchical growth, proving that the universe builds things from the bottom up, with collisions acting as the primary engine of construction at every level. How many other such cosmic matryoshka dolls are hiding within the tidal streams of other galaxies, their silent, beautiful violence waiting to be seen? A final, rasping breath echoes from a dying star. Object 42 is an OH/IR star, an elderly giant in its last, deeply obscured phase of life. This is not a star that shines brightly in the visible spectrum. It has retreated behind a wall of its own making. The name itself tells the story. The OH refers to hydroxyl, a simple molecule made of one oxygen and one hydrogen atom. The IR stands for infrared, the domain of heat. This star is so thoroughly cloaked in a cocoon of dust that its feeble visible light is completely smothered, and it reveals itself only by the warmth it radiates and the specific microwave whispers of its hydroxyl molecules. This stage represents a brief, final act for suns of a certain mass, a last dramatic performance before the curtain falls for good. The star itself is a pulsating variable, similar to a mirror star, rhythmically swelling and shrinking. With each expansion, its outer layers loosen, and powerful stellar winds carry away immense amounts of gas. As this gas travels outward, it cools, allowing tiny particles of silicate dust to condense like soot from a cosmic chimney. This dust forms the incredibly thick, opaque envelope that defines the star's existence, a shroud so effective it can block the star's visible light entirely. But within this dark, expanding shell, a fascinating natural amplifier is at work. The hydroxyl molecules floating in the vast envelope become energized by the star's infrared radiation. They are pumped up, ready to release that energy. When a passing microwave of the right frequency triggers them, they all release their energy in perfect sync, creating a powerful, narrow beam of microwave light, a natural maser. It is a coherent shout from within the silence of the dust, a laser-like signal that cuts through the galactic noise. What would it be like to approach this stellar elder? You would fly through a perpetual, blinding dust storm, a deep space blizzard of the star's own expelled substance. The central star would be utterly invisible, a hidden heart beating within a dark, warm, and noisy cloud. This entire structure is a fleeting factory. The star is manufacturing dust on an epic scale, enriching the galaxy with silicates and other heavy elements that will one day become the raw materials for rocky planets. In a few thousand years, the star will finally shed its entire outer envelope, revealing its hot, dense core as a white dwarf. The magnificent dusty shroud will drift away, illuminated by the ultraviolet light of the exposed core to form a new planetary nebula. For now, the OH/IR star stands as a deeply hidden, yet brilliant testament to a star's final, productive act of cosmic recycling. A dead star feasts on its living neighbor. This high-mass X-ray binary is a system of cosmic vampirism, where a dense stellar corpse, either a neutron star or a black hole, orbits a massive, brilliant companion. The normal star, a blue giant many times the mass of our Sun, is constantly buffeted by its own powerful stellar wind, a relentless gale of particles blowing from its surface. But the dead star's gravity is so immense it acts as a celestial siphon, pulling this stellar wind directly toward itself. The captured gas does not fall in a straight line. Conserved angular momentum forces it to spiral inward, forming a superheated, frenetically spinning disk of plasma around the compact object. This is the accretion disk, a whirlpool of doomed matter reaching temperatures of millions of degrees. It is in this maelstrom, just miles from the surface of a neutron star or the event horizon of a black hole, that the material glows with an intensity that floods space with high-energy X-rays. What would it be like to witness this process up close? The accretion disk would be a blinding, flat pinwheel of incandescent fury, its inner regions shining with a harsh, lethal light. The neutron star itself, if that is the predator, might reveal its presence through a rapid, clockwork pulsation as its intense magnetic fields channel the incoming material onto its magnetic poles, creating brilliant, flashing X-ray hotspots. The system is a perfect balance of power and delicacy. The feeding process is not always smooth. Clumps in the stellar wind or instabilities in the disk can cause the X-ray output to flare and flicker erratically, a visible sign of the chaotic dinner happening in real time. This violent relationship is paradoxically a stable one. The two stars are locked in a gravitational embrace that can last for millions of years, one slowly being consumed to fuel the brilliance of the other's grave. How many such deadly dances are playing out in the galaxy, their silent, high-energy screams revealing the final fate of so many stellar partnerships? A faint, dusty halo encircles a mature star, a silent graveyard of cosmic ambition. This debris disk is the leftover evidence of a solar system's violent youth, a sprawling ring of pulverized rock and ice that never managed to coalesce into a full-fledged planet. It is the scattered building blocks of a world that never was, a permanent record of creation stalled. The individual particles are tiny, some no larger than grains of sand, but collectively they form a vast celestial junkyard stretching across billions of miles. This dust is not a pristine remnant, however. It is a dynamic, ever-changing environment. For the disk to remain visible after billions of years, it must be constantly replenished. The primary source is a relentless, slow-motion demolition derby happening in the darkness. Asteroids and comets within the disk are constantly colliding, their impacts grinding each other down into finer and finer dust, a perpetual cycle of destruction that feeds the faint, glowing ring we observe. What would it be like to venture into this region? The space between the dust grains would be vast, but the sky would be utterly alien. Instead of the clean, black void of our own solar system, the heavens would be filled with a permanent, faintly luminous fog, a zodiacal light so intense it would outshine the Milky Way. The central star would be a hazy orb, its light perpetually reddened and dimmed by the endless, orbiting dust. This disk is more than just a collection of rubble, it is a profound clue. Its very existence strongly implies the presence of unseen, shepherding planets. A smooth, uniform disk would naturally spread out and dissipate over time. The fact that this one maintains sharp, defined edges suggests the gravitational influence of hidden worlds, their orbits acting like cosmic spatulas, confining the dust into a specific band. Gaps within the disk, much like those in a protoplanetary disk, could be the calling cards of planets clearing their orbital paths, their presence revealed only by the emptiness they create. This dusty ring is a frozen moment in time, a middle chapter in the life of a star. It tells the story of a system that successfully formed, but whose construction phase left behind a permanent, glittering scar. How many other such mature stars are also ringed by the evidence of their own chaotic past, their hidden planets waiting to be discovered by the shadows they cast upon the dust? A galactic fountain is spraying the raw ingredients for worlds high above the Tadpole's starry disk. This is not a gentle mist, but a colossal geyser of million-degree gas, erupting from the galaxy's plane and arcing through the darkness before raining back down in a continuous, life-giving cycle. The engine for this immense fountain is the collective fury of stellar death. Throughout the spiral arms, supernovae are constantly detonating, each one a titanic explosion that injects a bubble of searingly hot gas into the interstellar medium. These individual bubbles merge and rise like blobs in a cosmic lava lamp, buoyed by their own tremendous heat. This hot gas punches through the cooler layers of the galactic disk, streaming upward into the halo in vast ionized plumes. What would it be like to witness this upflow? You would see a river of incandescent plasma, glowing with the faint light of ionized oxygen and nitrogen, flowing silently and ceaselessly into the void above the galaxy. But the journey does not end there. Gravity is a patient force. As this hot gas travels far from the energetic disk, it begins to radiate away its heat, slowly cooling over millions of years. As it cools, it condenses into denser clouds that eventually succumb to the galaxy's pull, falling back down as a shower of cold, metal-rich rain. This returning downpour is the most crucial part of the entire process. The gas that originally erupted was seeded with heavy elements forged in the hearts of those exploding stars, elements like iron, oxygen, silicon, and carbon. When this enriched material falls back, it sprinkles the galactic disk with the very stuff of planets and life. It is the universe's most fundamental recycling program. The spiral arms are not just creating stars, they are fertilizing themselves for the next generation. Without this fountain, the galaxy would eventually exhaust its usable gas, or it would remain locked in a thin, unproductive layer. This cyclical flow constantly churns the galactic environment, stirring the pot and ensuring that the ingredients for new solar systems are thoroughly mixed and widely distributed. How many of the tadpole's strange objects owe their existence to this endless, invisible rain? A gentle fallout from a storm of cosmic violence, a razor-sharp line of fire cuts through the darkness of the tail. This tidal shock front is a glowing, cosmic wound, the precise boundary where the galaxy's stolen material is fighting for its life against the void. The tadpole's tail is not drifting through empty space, it is plowing through a thin, invisible mist of intergalactic gas, and the collision is violent. Think of a speedboat cutting across a still lake, its bow pushing up a sharp, foaming wave of water. The tidal shock front is that bow wave, but on a galactic scale. The gas at the very leading edge of the tail is being abruptly slowed and compressed, squeezed so violently that its temperature skyrockets to millions of degrees. This compression heats the gas until it glows with a fierce X-ray brilliance, creating a distinct luminous edge that traces the entire shape of the collision. What would it be like to approach this boundary? You would cross from the relative calm of the tail's interior into a searing wall of superheated plasma, a continuous, silent thunderstorm of atomic collisions. The shock front is a cosmic forge, a place of immense pressure and energy that can trigger spontaneous star formation. Dense knots of gas caught in this galactic pressure cooker can be squeezed past their gravitational limits, igniting into brilliant new suns right at the edge of oblivion. This glowing line is more than a static scar. It is a live demonstration of the galaxy's ongoing interaction with its environment. The tadpole is not an island, it is a traveler, and its journey through the tenuous medium between galaxies leaves a brilliant temporary wake. How many other galactic travelers bear this same glowing scar, a testament to their motion through the silent, invisible currents of the cosmos? Two stars have become locked in a dance of mutual dependency, a celestial pact where one star's waste is the other's fuel. This symbiotic system pairs a puffy, aging red giant with a small, intensely hot white dwarf, both enveloped in a beautiful, turbulent nebula of their own shared making. The red giant is the provider, continuously shedding its outer layers in a slow, dense wind of hydrogen-rich gas. Drifting through their shared space, this stellar wind is captured by the white dwarf's powerful gravity, funneling material onto its scorching surface. The result is a slow, steady simmer of nuclear reactions on the white dwarf, a constant, low-level burning of stolen hydrogen that makes the system glow with an unusual combined light. But this delicate balance is not stable. The white dwarf is a fussy eater. It cannot always process the incoming stream of gas smoothly. When too much hydrogen accumulates too quickly, it triggers a runaway thermonuclear explosion on its surface. This is not a full-blown supernova, but a nova outburst, a violent flash that suddenly increases the system's brightness 10,000-fold. The entire nebula lights up from within, fluorescing with the energy of the blast before slowly settling back to its normal state as the cycle of theft and digestion begins anew. What would it be like to witness such an eruption from a nearby world? The night sky would be violently rewritten in an instant as a new, brilliant star flares to life, outshining all others for a few glorious weeks before gradually fading back into obscurity. This relationship is both creative and destructive. The nova outbursts, while spectacular, also enrich the surrounding nebula with heavier elements forged in the blast. The entire system is a self-contained ecosystem, a cosmic symbiosis where two vastly different stars are bound together, their fates and their shared atmosphere forever intertwined by gravity and fire. How many other such volatile partnerships are hidden within the galaxy, their quiet cooperation punctuated by these brilliant, predictable tantrums? This ghost of a galaxy is almost entirely invisible. Drifting on the outermost fringe of the tadpole's gravitational influence, a low-surface brightness galaxy hangs in the void like a cosmic phantom, a wisp of stellar smoke so faint it barely registers against the blackness of space. It is a galactic paradox, an island universe of immense size and mass that possesses almost none of the brilliant stellar cities that define its brighter cousins. If you were to fly through it, you might not even realize you were inside a galaxy at all. The space between its scant, ancient stars is so vast that the night sky from any hypothetical planet would be a near-perfect black, punctuated by only a few lonely, aging suns. The profound dimness of this object is not due to distance, but to a fundamental lack of starlight. Its stars are spread so thinly that their collective glow is less than the background light of the universe, making it one of the most difficult classes of objects to detect in the entire cosmos. So how can something so dim be considered a galaxy, and what is holding this faint collection of stars together? The answer is a gravitational anchor of unbelievable proportions. This galaxy is composed almost entirely of dark matter. The visible stars are mere trace markers, a handful of glittering dust scattered across the surface of an immense, invisible ocean. The dark matter halo that constitutes its true body provides the gravity to bind the stars, yet it offers no light of its own. Its discovery forces a profound question. How many of these cosmic ghosts have we been missing? Our census of the local universe is built by counting bright objects, the brilliant spirals and ellipticals that are easy to see. This low-surface brightness galaxy suggests that our neighborhood might be teeming with silent, dark neighbors, galaxies that have been hiding in plain sight all along, their presence only betrayed by the subtle tug they exert on the light from more distant quasars or by the faint, smeared glow of their few resident stars. This object challenges the very definition of a galaxy and forces us to wonder if the universe is far more crowded and far darker than we ever dreamed. A faint, diffuse glow of pure energy permeates a forgotten quadrant of the tadpole, a whisper of gamma rays with no voice to call its own. This anomalous source is a cosmic ghost, a large and patchy region that shines in the most energetic light the universe produces, yet it stubbornly refuses to be tied to any known object. We have mapped the locations of pulsars, the remnants of supernova, and the jets of black holes, but none of them align with this persistent high-energy fog. Its very existence defies our catalogue of cosmic engines, forcing us to consider possibilities that lie at the very frontier of physics. One compelling and deeply mysterious explanation is that we are seeing the indirect signature of dark matter. The leading theoretical candidates for this invisible substance are WIMP, weakly interacting massive particles. According to some models, when two of these particles collide, they can annihilate each other in a flash of energy, producing secondary particles that decay into the very gamma rays we detect. This faint, diffuse glow could be the first tangible evidence of dark matter particles destroying themselves in the quiet, dark spaces between the stars. It would be the ghost finally revealing its presence not by its gravity but by its self-annihilation. The alternative is no less profound. We may be looking at an entirely new class of cosmic accelerator, a natural particle collider operating on a scale we do not yet understand. Perhaps collections of millisecond pulsars, too faint to see individually, are collectively flooding the region with gamma rays. Or maybe immense shockwaves from ancient, overlapping supernova are re-accelerating particles to energies that dwarf our most powerful man-made colliders. This source is a blank spot on our map labeled "Here Be Dragons," a challenge to our understanding of how energy is generated and distributed throughout a galaxy. Its diffuse nature makes it impossible to pinpoint, a shimmering cosmic mirage that offers answers to our biggest questions, but only if we can first decipher its elusive, energetic language. Is this the long-sought signal from the universe's most mysterious substance, or simply a new type of cosmic weather we have never learned to forecast? The answer is written in gamma rays, waiting for us to learn how to read it. Our final object is a cosmic chimera, a single point of light that refuses to fit into any drawer of our celestial cabinet. It flickers with the rapid, clockwork pulse of a neutron star, yet its radio signature is as smooth and featureless as a quiet black hole. It emits a steady, powerful glow of X-rays like an ultraluminous source, but its visible light spectrum contains the unmistakable lines of a surrounding nebula, something no isolated compact object should possess. This one source appears to be a pulsar, a black hole, and a nebula all at once, a combination of traits that current physics says is impossible for a single entity. It is as if the universe took the blueprints for three different cosmic engines and crumpled them into one. Every time we point a new instrument at it, we receive a conflicting set of data, a jumble of clues that point in every direction at once. Is it a pulsar whose intense magnetic field is somehow masking its own pulse? Could it be a newly formed magnetar, so young and wild that its behavior defies all our models of how these objects should act in their infancy? Or is it something entirely new, a type of stellar remnant or a stage of evolution we have never before witnessed and have not yet even named? This point of confounding light is the perfect conclusion to our journey because it embodies the very essence of the Tadpole Galaxy. It is a reminder that for every 50 strange objects we catalogue and study, there will always be a 51st that shatters our expectations. This galaxy, forged in a violent merger, is a crucible of the unusual, a place where the normal rules of physics are not broken but are constantly being rewritten. The greatest promise of this final frontier object is not the answer it will one day provide, but the profound and thrilling mystery it represents right now. It assures us that the cosmos is far stranger, more complex, and more wonderful than we have yet dared to imagine. From stellar newborns cloaked in dust to phantom galaxies woven from dark matter, the 50 wonders we have explored reveal a cosmos of breathtaking variety and constant surprise. The Tadpole Galaxy is far more than a single oddity. It is a living archive of cosmic processes, a place where the violent, the beautiful, and the inexplicable exist side by side. Within its chaotic heart and its immense streaming tail, we find stellar nurseries blazing with blue light, solitary worlds cast into the abyss, and the quiet, persistent signals of forces we are only beginning to understand. This menagerie of the strange is not a random collection, but a single, interconnected story written across billions of years, a story of collision, rebirth, and the relentless creativity of the universe. It serves as a unique laboratory, a nearby window into the most extreme physics and the most delicate acts of creation, challenging our assumptions at every turn. Each object, from the runaway star to the ghostly hydrogen cloud, adds a crucial piece to our understanding of how galaxies live, evolve, and ultimately shape the emptiness around them. Now we turn the question to you. With this journey through 50 cosmic mysteries complete, which of these strange inhabitants captured your imagination the most? Was it the ticking time bomb of the luminous blue variable, the silent enigma of the dark matter halo, or the perfect geometry of the Einstein ring? Share your thoughts in the comments below and let us know which object you believe holds the key to the next great cosmic discovery. Billions of years from now, the Tadpole Galaxy will be unrecognizable. Its magnificent tail, that river of cosmic orphans and drifting hydrogen, will not simply fade away. Instead, it will become a cradle. The immense self-gravity of the largest knots within it will finally overcome the tidal forces that created them, and these clumps will contract, pulling in the surrounding gas to ignite their own first generations of native stars. The green pea fragment will be one of the first to succeed, blossoming into a true dwarf galaxy, a small, independent satellite orbiting the now middle-aged giant that was once its parent. The hypervelocity runaway star, along with countless other intergalactic tramps, will by then be utterly alone in the profound black, their journeys having taken them far beyond the reach of any galactic light. The brilliant, chaotic core will have long since exhausted its ferocious starburst. The blue blobs will have burned out, their massive stars having exploded eons ago, and the frantic ring of star-forming fire will have dissipated, its massive stellar siblings long dead. The quiet supermassive black hole binary at the center will have finally completed its slow gravitational waltz, merging in a cataclysmic event that sent a thunderclap of gravitational waves across the cosmos, leaving behind a single, more massive, and perhaps now active black hole. The planetary nebulae will have faded, their glowing gas dispersed into the interstellar medium, and the recurrent nova will have fallen silent, their white dwarfs cooled to black dwarfs or consumed in final, violent explosions. This future transformation is not an end, but a continuation of the cycle we are witnessing today. The Tadpole's fate is to become a more common, settled elliptical galaxy, its distinct shape erased by time, its strange objects either normalized or extinct. Yet in that future calm, the seeds it sowed in its tail will be thriving as new galactic societies, each with its own future mysteries. This cosmic life cycle, from violent collision to quiet maturity and new birth, is the true story of the Tadpole. It is a powerful reminder that we are not looking at a static portrait, but a single frame in a billion-year movie, a fleeting glimpse of a universe in constant magnificence.